application of thermal phase shifters in a silicon photonics process. My name is Shayan Reza, an electrical engineering major from Vulture College. My mentor was Optical, and my faculty advisor was Professor Clint Scow in the Department of Electrical and Computer Engineering. My research was funded by the Institute for Energy Efficiency, and their mission is to develop new technologies for a sustainable energy future. So, data centers are the powerhouse of the internet. So they're essentially just a bunch of computers that store, process, and distribute information. But unfortunately, the current state of data centers are not very energy efficient due to switching between electrical and optical power. So the consumption of data will only increase in the future, and so current data centers will not be able to handle that. In fact, global data traffic is expected to increase by a factor of 4.5 from 11 exabytes. For reference, 1 exabyte is equal to 10 to the 18 bytes per month this year to 49 EB per month in the year 2020. So in order to fix this problem, we are creating an all-optical photonic switch. And the reason for this is because optical fibers are a lot faster than electronic cables. They contain a larger bandwidth and are more energy efficient. So my project focused on testing the efficiency of different heaters of different geometries. And the heaters are a vital component in the switch because they will be tuning to the ideal wavelength in order for the device to perform at its optimal efficiency. So my goals this summer were to characterize the efficiency of the heaters and determine how much power is needed to go into the system. We wanted to get away with putting in as little power as possible, and as well as to identify the optimal heater structures. So because the heaters are of different dimensions, they will generate different resistance. So, and we don't know what the ideal is for that. So that's what my objective was, to figure out which design is the most efficient. So this is the device that was designed by my mentor, the structure of the device that was designed, and then this is the structure that I tested. So in order to measure the efficiency, we measured the resistance of the heaters and thus finding the tuning efficiency. So the heaters are located on a Mach-Zehnder interferometer, and so a Mach-Zehnder interferometer, or an MZI, is a device that measures phase shifts. So the light is coupled into the waveguide, and then it splits at this part of the MZI and then travels along both of the arms and then recombines here. So the heaters located along one of the arms, they change the index of refraction, which will change the path length difference of which the light takes along the arm. So I took tungsten probes and made contact with the electrical probe pads that are attached to the heaters. And once I made contact, I ran current through a tunable laser and did a voltage sweep. So in order to minimize the amount of optical or power loss in the device, we do optical fiber alignment. And so the better the fiber is aligned into the waveguide, the less power loss will be in its surroundings. And so this is the waveguide that I coupled that into, which then went into the Mach-Zehnder, which I tested on. So these are the results of the measurements that I took on the heater structure. So I plotted current versus voltage, and I calculated resistance from that. So resistors 1 to 11 and 12 are the same width and length, and so you can see that they have a different slope compared to the other heaters. And so I also did a voltage sweep from 0 to 15 volts for resistor 3, and so you can see how fast the optical power changes within varying wavelengths. And you can see at this point, such as 1549.5 nanometers, how with different voltages there's like different dips in the power. And so this is just for an example for one of the resistors that I tested on. And so in order to find the efficiency of the different resistors, because they are of different geometries, we took a snapshot of the heaters at 1549.5 nanometers, and we found the optical power that changes within that wavelength. You can see how resistor 6, if you look at resistor 6, that is the most efficient because there is less optical or less power loss within the power input that we were putting into the system. So our conclusions were that smaller heater geometries tend to generate more heat, which is more efficient for the optical switch. And so in the future, we hope to continue to test the heaters of varying dimensions to find the optimal heater structure for the switch. So I'd like to thank my mentor, Takako Yurikawa, for her guidance this summer, as well as to Professor Tetsugawa for his support and allowing me to work in the lab. I would also like to thank Yagi for running my research, and then Wendy and Lance for their support and feedback.